Welcome to the most comprehensive guide of how to build an AI brain for business so that this system turns their messy data into extra revenue. Now this video is for an AI brain for specifically a car dealership. There will be no gatekeeping. I will tell you everything and provide you with the code that anybody can download for free so that you can build this system on your own. And because my background is AI research and development to provide actual, real added value, this project will be treated as a research and development project. Now this video is for two kinds of people. Either you're a business owner and in this case you want to discover the added value of such systems to your business, or you are curious to know what goes behind building those kind of systems, or you are an AI developer and in this case you would like to know how to build these systems and you don't want to waste time, searching for such information. This video combines my previous ones about the same project so that you can watch everything without any interruption. And don't forget guys that to access the full code, it will be via the link in the description. Let me show you the end result before we get started. So it will look like this, where you will be interacting with an AI conversational agent and you will be able to ask questions like this. Do you have black SUVs with heated seats? And then after some time, it will have an answer. Yes, we have a black 2020 Mitsubishi Outlander and so on. Another question could be, what's your cheapest Mercedes? And then after reading the answer, you can see the stats here, where you have the response time. For example, here it's 2.44 seconds, how many documents or listings were used, the cost per query, as well as the number of tokens used. And because I hate when in the beginning of YouTube videos they tease you about what's coming up next, I will guys tell you what's the final AI system that I used. I basically use Gpt-OSS 120B for the retrieval parts with 94% of recall, the same model for the generator with 80% of score answer, an average response time of 2.8 seconds per query, and an end-to-end cost of $0.001 per query. So if you're curious to know how much extra revenues this system can bring to a business, as well as how did I came up with this final config, keep watching. What we'll be covering first is the business use case, then we'll go over why this is an AI research and development project, the web scraping part, obviously building the RAG pipeline, and finally the user interface integration. So let's get started. First, let's do a quick recap about what is a RAG. Basically, a RAG stands for Retrieval Augmented Generation, and what it means really is about building the AI brain of a business. Imagine like an AI system that knows the data and procedures of a business, and then people will ask it questions. It can be like employees or customers asking this system questions, and then this RAG will go and fetch information in this data and then answer back like something as specific and accurate as possible. So basically it's about combining the unique data of a business plus the intelligence of like LLMs like ChatGPT and Gemini to answer something in an accurate and specific way. That's pretty much it. Now let's move to the business use case and return. Basically, the use case is the following. Imagine a car dealership wants to set up an AI speed to lead system. And basically why I'm saying this is that I had a discussion recently with the car dealership in the US and they wanted to do exactly that. So basically what they want is to launch a paid ad campaign on Meta, and then each ad will be for a specific car. And the objective is to contact the lead who opts in as fast as possible, because the more we are slow, to follow up, the lower the conversion rate will be. And basically the leads will be contacted via an AI voice bot, and there will be like a RAG attached to this voice bot. And the goal basically is to book a test drive with the lead. So that's pretty much it. Basically, launching an ad campaign and contacting the leads as fast as possible to convert them into a meeting. Now, you might be asking, why do we need a RAG system for this? So basically, the RAG system will be like one component from this whole project, but there are three main reasons why do we need a RAG. First, it is a zero maintenance system, because basically, you know, when you have car dealerships, the inventory changes all the time. Cars get bought and sold all the time, which means that if we have a system that knows all the time our inventory, we can quickly, you know, launch a new meta ad campaign for new cars, you know, so we don't have to every time like change things or like build a new system. It is set up and it is done. The second reason is that the leads, they rarely stick to one car. So you know, during a conversation, you will have a lead that will say, hey, actually, do you have anything cheaper? Or maybe he will say, actually, I have a little bit more budget. Can we go for a similar car with more options? Or, hey, I'm also considering black SUVs apart from this specific car. Do you have something within the same price range? You know, and having a system that knows about all the inventory will be super useful to increase the conversion rate. And the third reason why do we need a RAG is about future proofing. So basically, once the RAG will be in place, it will be reusable for so many things. We could imagine like setting up a chatbot on a website, you know, that could answer questions of the leads. Or we could have omni-channel customer support. Imagine like this car dealership has like a Facebook page, an Instagram page. We could incorporate this chatbot and conversational agent into these pages so that they can answer the leads as fast as possible. And of course, this RAG system could also serve as like an internal tool for sales employees. So let's say like a lead walks into the physical location and then they start asking plenty of questions. So maybe, you know, the employee can open up this tool and then start asking it, hey, do we have like black SUVs that are Ford under $30,000, something like that, you know, and the tool will quickly fetch information and answer accurately. So I think you have guessed this by now. The main business outcome that we want is to make more sales. Basically, we want to incorporate the RAG into a system that will help us sell more cars per month. But now we'd like to quantify how much we can make by setting up this AI speed to lead system. So basically, I came up with some approximations using some reasonable numbers, you know, for cost per lead and booking rates and so on, that works within the car dealership industry. So let's assume we will be using a $2,000 monthly ad budget for this meta ad campaign, and the cost per lead will be about $10. And this is a very reasonable amount for this industry, which means that on average we'll generate around 200 leads per month. Then here I wrote a voice AI reach of 90%. Because let's assume that not everybody will put like the right phone number. Sometimes they will make a mistake, sometimes they will just write the wrong number, sometimes there will be a foreign number that we can't reach. So let's assume that the voice AI reach is pretty high because, you know, as soon as the lead opts in and fill up his information, he will receive a call. So there is no reason he would be busy, you know, or something like that. So we end up with 180 leads that are reached. From there, we assume a 20% appointment booking rate for the test drive, which means that we would book 36 people. Then we just assume that there will be like a show up rate of 70%, which means that here 25 people will come up into this dealership to test the car. And let's also assume a closing rate of 20%. Here this is a pretty pessimistic scenario because I've seen that on average it is about 1/3 of the people that are closed, which means like normally it would be like 33.3%, but here I just said let's set it up to 20%. This would correspond to 5 cars sold every single month. And then here again I assume that we have an average profit per car of $2,000. And again, this is also pessimistic because I've seen that on average for used cars, the profit is about $2,500. So 5 times 2,000, we come up with 10,000 gross profit monthly for these AI speed to lead systems that incorporate this RAG system. Now, the car dealership that we're going to apply this RAG system for is called Premium Cars Florida. And this is their website. As you can see, this is the typical car dealership website that you will find with like featured cars and all type of financing options and so on. The reason I chose this dealership specifically is that first, they have a very good Google reviews on Google Maps, more than 1,600 reviews and 4.7 stars, which is very good. But the second reason, and more importantly, is that if we go to their website and then we type /robots.txt, we come up with this web page here. We can see the instructions for the bots that crawl the internet. Usually those are Google bots, we can see how they should behave. So basically here it says that any type of user agents, so any type of bot, they are not allowing those bots to crawl this web page, which actually corresponds to the admin dashboard of WordPress, which is a good sign, which means that they allow the listings, to be crawled. And more importantly, they have a sitemap. So a sitemap is this link here, as you can see, that actually makes it super easy for the bots to crawl all the listings. And the objective of this is that first, it makes it easy for Google to rank the website on Google, basically. And the second reason is that it makes it super easy for us to do web scraping, because in this web page here, we would have a list of all the listings for all the cars, and then it will be super easy to build a bot to crawl all over this data. Now, moving on to why this is an AI research and development project. So the first reason is super simple, is that the business outcome is super clear, which is about increasing the sales, right? But the technical part is not, because basically we do R&D when we want to achieve a business outcome, right? But we need to go through experiments to test which technical solution will be the best. And basically we want to discover which RAG pipeline will perform the best in terms of some metrics that I will talk about. And also, as I say here, we have multiple viable technical solutions, because whenever we want to build a RAG system, we don't have a one-size-fits-all, because there are multiple moving parts in every single step of building a RAG system. We can have multiple retrievers, different LLMs like ChatGPT, Gemini, some open source ones, right? We also have different chunking strategies and knowledge representation. And all of those things here, they affect the accuracy, the latency, and the cost per query. So all those three things are called metrics, evaluation metrics, that we'll use to evaluate the RAG system that we'll be building. So basically, what I mean here is that all the possible solutions, there are multiple combinations of things that we can put together to get a RAG system. And every single time we assemble those Lego blocks together, we'll get a unique pipeline that we need to test. And this unique pipeline will give us different metrics in terms of accuracy and so on. That's why we say that we need to follow a R&D process, which is iterative, to get our final system, basically. Some other important reasons why this is an R&D project is that RAG plus voice is an uncharted territory. We have still things that are coming up every single day in terms of technology, and we're still figuring out how to build those systems in the best possible way, because we need to manage the latency, because when the AI voice bot will call the lead, this bot needs to know everything about the inventory of the dealership, but shouldn't feel like we're talking to an AI, right? It should feel supernatural. And also we need to manage the context, because let's say in a conversation, the AI and the lead are discussing some black SUV, right? Some Ford. And then they're discussing the specs and so on, the price range, the financing options and so on. And then moving on to like another brand, I don't know, maybe a BMW, and they also discuss some stuff about this model and so on. And then the lead wants to go back to the first model because he wanted to ask a question. Hey, can I don't know, have some automatic option on it or something like that, Well, the AI needs to know about the context and needs to remember what was discussed before, And all of this needs proper management. The last reason why this is an AI research and development is always when it's about building some technical stuff, we'll have trade-offs. This is something that comes up all the time. And basically, we need to discover those trade-offs and choosing the right ones. So maybe it will be about faster responses versus more accurate responses, right? Or cheaper versus more natural. Or having low latency versus low context size, right? So we need to choose which trade-off will be the best for this particular project. Now we move on to the general steps that I will be doing for this project. The first one will be about data extraction, and this comes up in pretty much every single RAG project. We want to feed some specific data to the AI so that it will know from where to fetch the data to answer accurately. And since this data is available on websites, then we'll be relying on something called web scraping. It's about saving data that is accessible from the internet. I actually have a lot of experience, doing web scraping. I have done that during my master's. I have done that for some side clients. But basically, we'll go through either, using a tool, like a no-code tool, or just, coding that by myself, because I already have like code that is ready to be used for pretty much any type of project. And we'll see exactly how we'll do that. The second step, and for me, the most important one, is about building an evaluation data set. Because, at the end of the day, it's not about building something. It's about making sure that the thing that we build is super accurate and specific, So as I wrote here, it is super important to test the entire RAG pipeline. And basically, it's also about making sure that this system prioritizes accuracy over sounding useful, And we want that whenever we ask something and we don't have this data, or the AI doesn't know, it says that I don't know, but doesn't make up something or hallucinate something on the fly, right? We don't want this kind of behavior, right? So basically, building the evaluation data set will be about coming up, like crafting a list of questions and answers with varying levels of difficulty. To see whether, the AI is actually able to fetch the right data and answer the right answers, basically. The first type of question would be easy. So they will involve a direct lookup into the data set. An example of this would be, what's the price of the 2022 Toyota Camry? Or does it have a sunroof, right? So this will be super easy to answer by an AI. The second type of question would be of moderate difficulty, and those would involve multiple contexts. And examples of that will be which of your SUVs are under $25,000? Or do you have any electric cars in stock? And basically for this question, it will have to go over all the SUVs in the inventory and then compare them in terms of price range and then generate the answer. We also have hard questions, and those will be involving advanced reasoning and implicit context. Some examples could be, what's the cheapest hybrid you have right now? Or which cars have similar mileage to the blue Civic, you know? And we'll also have a special type of questions that involve edge cases. So for example, do you sell motorcycles? We know that the answer will be most likely no, because this is a car dealership, right? So we do that on purpose to test whether the AI will be hallucinating something, right? Or we also have questions like, do you still have the 2021 model when no one exists, right? To also double down on it and double check whether the AI will be hallucinating or not. So this is very important to also include those type of questions in the evaluation dataset. And then obviously the next step will be about building the actual RAG pipeline. So, you know, when we have a RAG, we generally have two steps. The first one will be about retrieving the information, you know, basically fetching the right type of information within our data set, but also the generation part, which is about using the LLM to generate the answer. And we have multiple moving parts in each of those parts here, and we can, you know, go over many things to build our final RAG system. The next step will be about the evaluation. We have many ways to evaluate a RAG system, and one of them are called RAGAs, which is a framework to test the accuracy of this RAG system. And then the next part will be about the enhancing, you know, basically enhancing those parts, because, you know, we'll be following like a scientific method, meaning building something, testing it, enhancing it, and then so on. And so on and so forth, until we have something like super accurate for our business outcome. And finally, once we'll be super happy with our final system, we'll be doing the integration of the system to a user interface. So basically, we'll be building like a simple web interface where we can ask our questions and then the AI will generate the answers. First, for the web scraping, my goal was to use tools that are like super fast to use or that are super cheap or very cost efficient, you know. And basically, I looked at multiple AI scraping tools online. I went ahead on YouTube and I just looked for AI web scraping tool, and I found this first video. This tool, Thunderbit, seemed nice at first, but then they said that it is only free for the 6 first pages, you know, and then it becomes like a subscription of either $15 per month or $38 per month. So this tool was quickly discarded and couldn't be used for the project. Other than that, there is also this YouTuber that talks about using like DeepSeek AI to scrape any websites for free. And when I went through the methodology that he uses, basically what he does is that he uses like a tool called Crawl AI, and you gave it just like some URLs, and then it outputs the HTML, and then you need to use DeepSeek to interpret the HTML. It is not very good as a methodology, and it relies on DeepSeek, and you don't know all the assumptions behind this Crawl for AI. So basically, I ended up not using any AI tool. And what I did is that I used Selenium, which is a Python library. I'm super familiar with it, and it allows you basically to give you the tools to automate Chrome. So it can open Chrome, it can open any web page, right? And it can also perform actions within like a web page, either clicking on something or scrolling and so on. So it is super handy for automation and web browser automation in general. And after a lot of work, you know, web scraping the pages for this car dealership, I realized that it was the best choice in hindsight, you know, to choose Selenium. So for this web scraping, I had to do multiple steps. The first one was to read this sitemap.xml file to get all of the listings. And let me clarify what do I mean. First, we have the website that I told you about, which is premiumcarsfl.com. If you go to the website /sitemap.xml, it will go to this web page, and you can see here that we have multiple sitemaps URLs that we can use. We have post, page, and so on. And what we are interested into is this listing, because it contains all the listings that we need. And if you open it, you end up with this file here with all the possible listings that are available on the website, basically. And we have the first URL, which is the root page, and we don't need it. We only need all the other ones. Basically, if we do Control F and the listing / we can see that here at the moment we have 158 listings, but when I downloaded everything at that moment, there were only 151 cars, basically. So yeah, that's basically the starting point of the web scraping. This is an example of one listing. So it's a 2023 Toyota Corolla. It's a sedan with the price here, with the specs, And my methodology was to come up with some Python code that uses Selenium, right? To fetch all of this data, whether they are the specs, the description, the title, the price here, or the location, and then so that whenever everything here works, I can apply it to any listing, basically. All we need is an input, which is the URL, right, of the web page of the listing, and then apply the exact same code to every single listing. Now, the problem with this methodology is that for this specs part, this part here, I realized that it is, the data provided is not consistent. They don't all provide this type of data. Obviously, there is some data that is common across all listings. Obviously, the body style, the make, the model, the color, and so on. But some data types, are not provided. For example, here we don't have like the highway miles per gallon or the city miles per gallon. And this data is available for some other listings, and I realized this. So basically, we need to do some kind of dynamic web scraping. What I mean is that instead of, preparing, like telling Selenium to go directly to this localization and take the text, and then go to this localization and then take the text and so on, and do that for everything. What we need to do instead is to just look for this area, right? And then to loop over all the items, whatever the items are, because some, as I said, some will be provided and some will not. So basically, this is the methodology that I used. And what I ended up doing is that I created both a CSV file and a JSON dataset. The reason I did that is that I created a CSV file because after that, I can easily read the CSV file using Python, but more importantly, I can filter it, and do aggregation operations. For example, what's the average pricing of Mercedes or Toyota, or what are SUVs under 30,000 miles, we can do that very easily using CSV, basically. And also the advantage of using a CSV is that we have all possible columns, and sometimes obviously when there is the data, there will be like the row will be filled, and whenever we don't have the data, some columns will stay empty. However, for the JSON dataset, for every single listing, we have only the data that is provided. And I think I will end up using this dataset for, our embeddings for basically the next video. And guys, some tips. So the first one is about making the script wait before scraping a listing, because sometimes, you know, Selenium will want to go fetch some data before it has been loaded, you know. So there is like a very handy code that you can use that waits until all HTML elements have been loaded, you know, in Selenium before performing the fetching of the data. Also, there is an option called headless, which means we don't display the browser, you know, the window. We don't display it because it allows us to do the scraping in a much faster way. And basically, the second tip is about enabling this option if we want to speed up the scraping, because if we loop over all the 150 data samples, you know, we don't want the browser to open a new window every single time. It will be super slow, right? We want to do everything in the background, and we want it to be fast. We also need to disable headless option, you know, to check if some actions are done correctly. Normally, when Selenium opens like a web page, a listing, it will be shown that way, you know. And as you can see here, the description is not shown. We need to perform an action. We need to click on this show more so that it will reveal the rest of the description so that Selenium can scrape it. And basically, in order to double check that this action is indeed done by Selenium, we need to allow this, we need to disable, you know, this headless option so that it will actually open the browser and let us see and double check that the action has been taken. So this is just a tip, guys, to make sure that everything is performed as planned. Now I will go through a quick code review about the Python file that I wrote to do the web scraping. First, I wrote this function, you know, read the log tags, which will read this XML file. And let me show you guys the XML, how it looks like. So if you open this file in a text editor, you know, you will see something like that. Basically, you have URL tags, and inside every single URL tag, you have a lock. Basically, we need to extract the lock, which is basically the location, except the first one, right? So yeah, basically that's Python code that I just showed you. Just reads and parses this file and extracts every single URL contained here. This function here, getDriver, will just be used to start the Google Chrome bot, basically. I also coded the account token function because I was curious to know on average how many tokens like one listing would have. And basically, I just coded this, you know, out of curiosity, and I think the result was about 700 to 800 if we take into account the description, which is pretty long, as well as all the specs of a car. For me, one of the most important code snippets is this one, this part here, because first we are waiting, you know, until some elements appear, and those elements actually is the list of specs that I told you about. And here we are looping through every single element, and then, you know, basically adding that into a dictionary. And if you have noticed, I'm using XPath, which is basically a way to locate HTML elements within a web page. So basically, it's like a special type of language that we can use that libraries like Selenium understand to know exactly where to go fetch the information. And the most important code that you need, guys, is this function here, which is download data, CSV, and JSON. Because if you call it, it will download every single items contained in the XML file. And as you guys can see here, at first I was using every single location, you know, of every single spec to go and fetch it before, you know, realizing that the data was not consistent. So I just kept this part here commented. If you guys are curious to know if you would be able to get the XPath on your own and compare it, you know, with my own, yeah, you know, guys, feel free to reuse it, but at the moment it is just commented because it is not used. And this is, guys, a screenshot that shows how this will look like, you know, once it will start downloading. So basically, for every single listing, you will have processing, then the name of the URL, basically. And then once it is done, it will just print done and move to the next listing until everything is finished. Now, the next part is about building the datasets. And if getting the CSV output or the JSON file is pretty straightforward, as I have shown you, I also decided to build graphs out of the JSON file. The reason is that, as I told you in the first part, you know, of this series, I'm treating this project as a research and development project, you know, and we need to compare multiple alternatives, multiple approaches, right? And the first approach will be based on embeddings, chunks, and so on. And the second part, will be based on graphs, you know, and graph rags. So yeah, I also decided to build graphs using Neo4j and also Python to generate the Cypher queries. So Neo4j uses a specific language called Cypher to build graphs and query them. And actually, it was not that easy to do because Cypher needs a specific syntax, and you shouldn't, you know, include many types of characters when building any query. Let me show you what I mean. This screenshot here shows the Cypher queries that were generated via my Python script. So we have create, vehicle type, and so on. And as you can see, we have a syntax error, invalid input. So one of those characters were inside my query, right? And we need to basically clean the queries and sanitize them to make sure they don't include any of those characters. The second reason why this was not as easy as expected is sometimes, you know, you don't have any bug, everything is running smoothly, but you have what we call logical errors, and those need manual verification. And I will show you one example of that. So here you can see the graph that was created, you know, after the generation of the Cypher queries. But you can see here that we have a car that is of make Kia, right? And that has this listing, which is here. This number here is like the stock number of premium cars, like this car dealership, basically their inventory ID. But here the bug is that here we say is year 95,175, which is impossible, right? It should have been easier 2020, right? But actually, here is the number of miles of this listing of this car. So basically, what I mean is that even though you run the Cypher queries and everything works smoothly, you still need to manually verify that the data makes sense. Also, guys, another thing that I had to pay attention to is, you know, for this description of a car, as you can see, it contains a lot of emojis here. And here we can see this show less, which ended up being scraped too. And also we have multiple useless things like those websites, kbb.com, or here we can see +2, +1. Everything here that you can see creates noise and needs to be cleaned before being used in the dataset. Also, guys, a useful tip for building this graph is that, you know, once you have a graph that is ready, you want to visualize it because you want to know if it makes sense, you know. And basically, when you type the query to return all the nodes, sometimes it might be confusing or even misleading, and you might think, hey, this doesn't make sense. Maybe there is an error somewhere, right? So the best way to double check your data is actually to craft a special query, right? To just return a subgraph. So for me, for this example, what I did every single time I built like a different graph, I will just output all Toyota cars, you know, just display everything related to Toyota, and let me double check whether the pricing, the miles, everything makes sense and is contained within the original JSON dataset. And what I did is that I went ahead and built 3 types of graphs. So the way they change is that the schema, the structure of the graph changes. So the first one is about the vehicle, as the root node. Then they are linked to brands, so BMW, Toyota, Jeep, and so on. And then we have a listing, like a specific listing, and then we have all the specs of the listing. So the mileage, the body style, and so on and so forth. Let me show you how it looks like. By the way, guys, the queries that I will be using, I prepared them in a file called useful cipher queries.json, and those are the queries that I will be using to display, the nodes that I prepared. So, this query here is about showing all the nodes and all the graph basically that we built. This one is about deleting everything, so it is useful, when we want to go from one graph to another. This one is about visualizing the first type of graph, the second one for the second type, and this one for the third type of graph. So let me first show you what's different, when we decide to display everything versus when we want to display only Toyota cars. Here, this is what happens when we enter this query here. So let me resize this. And don't worry, guys, I will show you how to create this dataset because I also prepared the queries for you. But know that here at first it might seem, misleading because we have the feeling that every single listing, is like isolated. It is not linked to any like brand and so on. And basically the reason for this is that here, when we perform this query, we can see that not all return nodes are being displayed due to initial node display setting. This is basically just like a constraint to prevent your computer from processing too much data, because in some graphs we might have billions of nodes and edges, and just as a precaution, Neo4j is limiting us in the number of nodes that can be displayed. So obviously internally Neo4j will run some query, right? And it will just display the first 500 nodes that appear. And it might not make sense when displayed. That's why right now we'll be visualizing all Toyota cars. So you take this query, you copy it, you paste it here, and then you press play. So as you can see, it is creating a nice subgraph. Let's maximize this and then zoom in. As you can see, it is creating a nice subgraph where here we have the root node, which is a car, and we can see that it is of make Toyota, and then every single light blue circle here is corresponding to a listing, and we can see that it is linked from the Toyota via a has listing edge, and we can see that for this car, it is basically a 2023 Toyota Camry. It is gray. It has a price of $22,500 It is a sedan, and so on and so forth. So yeah, basically you can have every single information about a listing, and it is pretty nicely built using a graph. Now let me guys show you the code behind the creation of this first type of graph. It is linked to this function here contained in this file, listings to graph.py. So basically this function generates cipher query database 1. That's what it is creating this graph. And you can see here all the queries that we create, like create with the node, or here create the node with the relationship is make, and so on and so forth. So basically we need to loop through all the unique listings, also all the unique makes, right? And yeah, basically guys, feel free if you want me to prepare for you a cipher tutorial, please comment it below, and yeah, I will be super happy to do that. But basically the result is that after iterating over all the listings and creating everything into a string called a cipher query, we output everything into a JSON file called cipher queries premium cars Florida database 1. .json, you know. And let's open this file and see how it looks like. This is the file with all the Cypher queries, right? So as you can see, it has around 6,330 lines, right? So it is a lot. So basically, to create the graph, you just select all with Control A or Command A if you are on Mac, and then you copy it with Control C. And then you go to Neo4j. Here, since I already have a graph, I will have to delete everything before creating this graph again. So what I will be doing is that I will go back to this file called useful Cypher queries. I will copy this query to delete everything. I will paste it and run it. As you can see, it has deleted that number of nodes. If you want to make sure that everything has been deleted, you can run it again. And if it says no changes, no records, just know that nothing is in your database, basically. And now we go back to the queries generated. We copy them, paste them here, and then run this cell. To run it, either you click on this play button, or what I do also is Control Enter. It will take a few seconds, I think from 4 to 5 seconds to run, but if everything has worked as it is supposed to, it will say here, added 3,157 labels, and so on and so forth, about the nodes, the properties, the relationships, and so on. And yeah, after you do this, you will be able, you know, to either visualize this subgraph here for the Toyota, or visualize everything with match n, return n, this query that I showed you previously. The second type of graph that I decided to create is following this schema here. First, we go from the vehicle root node, then we go over all years, all possible years. Then for each year, we go through a make, and then the model, then the listing, and then the specs of a specific car. Let me show you how it looks like. Again, I will reproduce everything that I showed you to be able to create the second graph. So I will delete everything using this query. Go to the second file that was generated, copy it, paste it here. As a precaution, I will just close the window related to the first graph. Then I will run it. Then you should go to the second visualization Cypher query, right? You paste it here and run it. And as you can see, it shows a different type of graph. Let's zoom in and see how it looks like. By the way, here sometimes, guys, when you want to display something, the label of a node will not be shown, you know. And to show, you know, the labels, it's very easy. You just click on the node, right? And then you click on this button to reveal some options. You click again, and then here you just press the year, right? For the, I mean, this type of node is the year. So now you can see that once it is toggled, it is displayed. So as you can see, we have the root node, which is a vehicle of type car, right? Is year 2023, and then we have multiple makes. I mean, for this one, I mean, for Toyotas, we have only Toyota, obviously, and then we have multiple models. So either the Camry here or the Corolla, and for other years we have as well, you know, Corolla or Camry. Let me see if we have some other type of, yeah, and for, let me see, for 2020 we have a RAV4 as well. Here, guys, I tried to make everything readable so that you can read along, and as you can see here, it is very easy, you know, to know all the specs of this car. So basically, here, let's, as I told you, you know, all those light blue nodes, they correspond to a listing, right? And every single listing has a list of specs, basically. So we can see that as a body style, it is a SUV. The name is a 2020 Toyota RAV4, and so on. It is located in Miami. It has more than 100,000 miles, right? For the price, it is a bit less than $21,000. It has cloth, you know, as interior. You have everything about the spec. Now, the third graph schema is, you know, a vehicle. Then we have a body style, so SUV, sedan, and so on. And then we have a price range. Basically, I created this new feature of price ranges, you know, with the 10,000 increments. So basically from 0 to 10,000, and then from 10,000 to 20, and then 20 to 30, up to the maximum, you know. I think it was up to 40,000 USD. And then we have the listing and then the specs. So let's visualize this and see how it changes. Actually, there is a unique thing about this graph representation. So we go from the car to multiple body styles. So here we can have pickup, sedan, SUV, and so on. And then we go to the price range. But the thing is that here, you know, multiple body styles can point to the same price range, which makes sense because for 10K to 20K, we can have both SUVs and sedans, right? And this is called like a diamond shape in a graph. And basically, it will be interesting to see how this graph representation will affect the accuracy, you know, of our RAG system. And this is actually a research question because we don't know. We'll test and see whether it leads to more accurate results, no change, or worse results, right? So if we follow this arrow from 10 to 20K, this, contains this listing, right? Of, I think this is, this is a Toyota. It makes sense because we are visualizing all Toyotas. It is located in Miami. It has a price of 17,900 USD. So yeah, everything works well, and you will be able to download this code for free, guys. And concerning the code that creates this query, this is it. Right, this is generate cipher query database 3, and basically I go through almost the same logic as the two other ones. The only different thing about this one is that we had to use a function called discover price ranges, because first, you know, we have to loop over all the listings to be able, you know, to prepare the price ranges in advance so that we'll create them as nodes and then insert them into our graph. Now, after doing all of this work, you know, I was wondering, maybe there are some issues, you know, within this data set. So I just run like a quick check about something that shouldn't exist, which is duplicates in the VIN number. So basically a VIN number for cars is the unique ID of every single car in the US, in the United States, right? So there shouldn't be any duplicates, right? Or another check is about seeing whether we have duplicates in stock number, because the stock number, as I told you, is like the unique identifier of a car within this company, within this car dealership. So again, we shouldn't have any duplicates. And I found like a very super minor issue, and which were like 2 duplicates for the VIN, 2 duplicates for the stock number. I decided to not do anything about that because after I built the evaluation dataset, I realized that they are not contained in the evaluation dataset, which is important. So that's why, I didn't do anything about them. Now, going to the next phase, the evaluation dataset. Basically, I prepared 60 pairs of question and answers, and don't worry guys, I will show you how they look like via a Google Sheets file. And it was the most tedious part, it required a lot of manual work. I had to come up with good questions, high quality questions, and for every single question I had to produce code, to filter the CSV to go find the ground truth, related to that question, so that I can write in the corresponding answer basically. And another thing is that each question needs the corresponding context source, basically the number of listings that are needed to answer the question. And why do we need this? It's because we can check whether the RAG system is able, to fetch the data in the right way, right? And by preparing the right context source, we'll be able to double check whether this is the case or not. And guys, some tips to create a good evaluation data set. First, you need to come up with realistic questions. Imagine like a real lead that will ask questions to the AI. You need to come up with something very real, right? The second thing is that you need to prepare different degrees of difficulty. some easy questions, some hard questions, some medium level questions, and so on. We also need ambiguous questions because in real life, like a lead will ask ambiguous stuff that need interpretation. For example, what are some of your best SUVs under 20k mileage? You know, what does he mean by best? You know, or hey, do you provide financing for this Toyota Corolla? You know, what does he mean exactly by financing? You know, this is ambiguous. We also need questions that involve aggregation and filtering because let's say a lead asks, okay, what is cheaper? Your Mercedes cars or your BMW cars, you know? And this question, to answer it involves to first filter out all the BMW and Mercedes cars from the data set. So this is the first step. And the second thing is about aggregation. So computing the average price, which is like an aggregation operation over each brand, you know, and all those steps are required to answer the question in a correct and accurate way. We also need edge cases, questions that involve no data. For example, how much is your Rolls-Royce Phantom listed? You know, while there is no Rolls-Royce in the listings. So how will the AI behave, you know, if there is no listing, you know? We need to handle those type of edge cases. Another tip, you know, for preparing the evaluation data set is that for me, it could have been much faster if, you know, after generating all the questions, I would prepare some Python code where I would be calling like OpenAI API to generate a code for every single question. I will just look 60 times, you know, do 60 calls and then generate some Python code and then run it instead of coming up myself with the code. Now let's go through the Google Sheet. As you can see, this is the file that contains all the 60 questions, right? So we have the columns question, answer, the notes, you know, when I wrote something that I found useful, and the column context source. So let's go over some of the questions so that you just get the feel, you know, about this evaluation data set. So here I wrote ambiguous. What color is the Honda Accord EX you listed? And here the answer is that we currently have two Honda Accord EX listed. Here the question assumes that there is one Honda Accord listed, you know, while in reality there are two. So it involves some kind of ambiguity, right? So we need those type of questions. I like this question, what's the most recent SUV that you have under $10,000? Because as a note, I wrote trap. There is one SUV and one minivan where the body style mentions SUV, right? So basically here the answer will be our most recent SUV under 10K is a 2019 Mitsubishi Outlander and so on and so forth. But basically it shouldn't, confuse. It should take into consideration the title of the car as well, not only the body style, you know, of the listing. I also like this question. Show me the most expensive vehicle in your inventory. And this assumes that there is only one that is most expensive, right? But in reality, we have two vehicles that are the most expensive because their cost is the maximum and both have the same cost, which is $32,900. So yeah, it's a good question. Another question that is ambiguous is this one. Do you have any trucks around $25,000 with low mileage? You know, what is low mileage? And basically here I interpret it as mileage under 30,000 miles, right? Another interesting question, on average, how much does your BMWs cost compared to your Mercedes? And here this assumes that we have multiple BMWs and multiple Mercedes listed. And actually the answer is we currently have only one BMW listed, priced at X, while our Mercedes vehicles average around 21,800 USD. So guys, feel free to read the rest of the questions. I will just go through a last one which I found interesting because it involves like a real anomaly. It is this one. I saw a listing of yours in the title. It says 2019 Chevrolet Silverado, but in the specs it says it's 2020. So is it 2019 or 2020, right? And actually it is true, you know, it is a true anomaly because here in the title it says 2019, right? But in the specs here we can read 2020. So it doesn't make sense. It is a true anomaly that should be addressed. Now the code that I wrote, you know, to prepare this evaluation dataset is under the file named prepare evaluation dataset.py. And it is super messy, guys. Please don't judge me on that. But basically, you will be able to play with it, you know, to test. Here, for example, this function display answer from specs, it chooses filtering. So here for this example, I'm filtering using like the model column, and basically here we want all listings that are either a centra or an elentra, because here we have the or sign. Or this function again fetch data from specs. Basically I'm iterating over all the listings contained in the JSON file, and I have multiple filters. I mean, feel free to uncomment and check, you know, the answers, but the active one at the moment is find all cars that have cloth, you know, as interior fabric, and the AWD for the drive type, you know, and for every single of this car, print the name, the VIN number, the price, the URL, and so on. Even at the end, you know, I got tired by every single time creating a new function and then running it. I just, you know, created a vanilla function called sandbox, and I stuffed like a lot of logic here that I kept commenting out and so on. So feel free to use it if you want. First, let's see how RAG pipelines work. I found an image on the internet that is pretty accurate about how RAG systems work. So basically, imagine you have your data set. So for our project, it's our list of car listings, right? And then we have a query. So a query for our use case is, for example, what are some black SUVs that you have that are under 50K and that also have leather as interior? The first part is about building a retrieval system. The main goal of this system is to retrieve the documents or the car listings, right, that are the most relevant to answer the question accurately. And you could have multiple approaches, you know, for building your retrieval part, and we'll see more about that later on. And the second step is the generation. So basically we'll be using the relevant documents found by our retrieval system, and then we'll combine it with a prompt and then an LLM to generate the final answer of our question. And as you can imagine from this system, the most important step is the retrieval, because even if you have a perfect generation system, if you know, your retrieval is not able to fetch the relevant documents, you will never be able to answer the question correctly. And this retrieval part is measured via multiple metrics. So you have the recall, and I will tell you more about how do we compute it. We also have the speed and the cost per query. And obviously we have a trade-off between those three metrics. Obviously we want as much recall as possible, but we also want the fastest answer, right? But also the cheapest one. And for this part, what I did is that I kept it very simple. It means that I didn't use any heavy Python library like LangChain. I only used like the very minimal light libraries that are required, you know, to run those systems. So let me guys quickly tell you about how recall is computed. So imagine for like a RAG system, we have documents from A to Z that are our knowledge base. And in order to correctly answer a question, it needs documents A, B, C, and D, right? And then you go ahead and build like a retrieval system using LLM maybe or some other methods. And the retriever will identify documents A and B as the relevant ones. In this case, it means our recall is 2, so those 2 documents, over 4, which is all the relevant documents, which means it is 0.5. So now you understand that the recall is about the accuracy of this retrieval system, and we want this metric to be as close as 1. Ideally, it will be 1, right? But something around 0.9 or 0.85 is already pretty good. Now, moving on to the retrieval methods, first I will tell you guys about the list of the methods that I used, then I will tell you more about how each one works. The first one is called symbolic retrieval, meaning we use some LLM to generate Python code, right? And then the second one is called also symbolic retrieval, but for generating cipher queries. And then we use the naive RAG system, which uses the semantic similarity. We have another method called BM25. And then we have re-ranker methods. I used both a local one that I downloaded and then another one from Cohere. And obviously, I will also tell you about something that I considered at first, but I did not use, which is about in-context memory retrieval. And I will tell you more specifically about why I decided to not use this method. Okay, so for the first method, the symbolic retrieval, in this case Python, it is very simple. We first explain in a prompt what we want to do, and I will tell you guys more about the specific prompts that I used. Then we also add to the prompt the structure of the CSV file. We also add the question that we want to answer. And then finally, an LLM will generate some Python code that will filter and aggregate over the CSV. And then the final step is to execute the code to return the relevant documents. The second method is almost the same. We explain in the prompt what we want to do, and then we also add the structure of the graph, so the schema of the graph inside this prompt. We also obviously add the question inside this prompt, and then an LLM will generate the cipher query, right? And then we execute this query in Neo4j to return the documents. And obviously, you will be able to download the code, and guys, make sure that your Neo4j database is open when running the code, because you might think that there is a bug somewhere and so on, while in reality you just need to launch Neo4j basically. The third method that I used is the semantic similarity, which is just the naive RAG method that we all seen on YouTube. So basically we do chunking. In this case, we split all our data set into chunks of information. And in this case, for this specific use case, one JSON car listing will be one chunk because it's the chunking that makes the most sense. And then we transform each chunk into an embedding. And then save that into a file. And obviously, when we want to ask a question, we will also embed that question. And then the next step is to compute the cosine similarity between the embedding of the question and the ones of the chunks. And then this cosine similarity is basically like a metric that will have a value between -1 and 1. And then we select the relevant documents either by thresholding or by doing a top K. So thresholding, it means that I will select a value, for example 0.8, and any document that has its corresponding score greater or equal than 0.8, then we just consider it as relevant. That is the thresholding method. Other than that, we also have top K, which means I will select K equal 5. In this K, I decide that the 5 highest scores will be considered as the relevant documents. And if you have paid attention to the previous videos, you've seen that top K here is not appropriate because we know in advance that some questions don't have any relevant documents because the data is not in our data set, right? So what I did for this method is that I just simply used thresholding. Also, another thing is that at first I considered Pinecone, because many people talk about that it's a wonderful tool, it's very easy to use and so on. I tried to use it, but I stumbled upon some bugs, right? So yeah, it turned out to be a headache to configure. So I just used like a super simple method instead that doesn't rely on any like external like API and so on, I can actually show you the specific error that I got. As you can see, here is the pinecone request ID, and then I had like a dimension mismatch while I was just, running some simple code from their GitHub repository. So I was just like, okay, this is not fast and easy to use, so I will just go ahead and implement on my own, because at the end of the day, it's just cosine similarity, it's not rocket science. And don't worry guys, I will tell you more about the code that I used for every single method. Then the next method is BM25. So I had to use a Python library called rank BM25. It is very easy to install. This method relies on the frequency of the words inside your question, as well as the frequency of the words inside every single document. And then we do some comparison, and then we'll select some scores. The thing with this method is that the values of those scores is not predictable, so you just cannot apply a thresholding method where you will select like a value like 0.8 and then filter out the relevant documents. That's why we need to apply either the percentile or the top K method. And for the percentile, basically we'll just take all the scores that were computed, and then we'll apply a percentile of 90% or 95%, and then take all the relevant documents based on this percentile. The next method, as I told you, is the local cross encoder or also local re-ranker. I use this library, which is called Sentence Transformers, which is a Python library. I thought at first that it was easy to install, but it was not. Personally, I use Python 3.12 for all my projects, but here for some reason it didn't want to work using that version. So I had to basically install 3.10 Python version and then create a virtual environment inside of it, and then install this library and all the other required libraries. So yeah, just know that if you want to also run the code that I provide for this particular method, just install Python 3.10 and you will be good to go. This method is just about using a neural network that uses both the question and all the documents. And then a score will be given to each document. Again, similarly to the previous method, the score range is not predictable. So again, we'll be either using a percentile or top K, and for me, I use the percentile. The next one is Cohere re-ranker. So basically, it works like the same as the method before. However, here, since the scores outputted by the method from Cohere API, the scores are ranging from 0 to 1. So in this case, we can use the thresholding. The reason why I decided to use Cohere's re-ranker is that I saw in many forums on Reddit as well that it is considered very good, by many data practitioners. That's why I decided to use it. And then finally, I told you about this in-context memory retrieval. I considered this method at first. I even wrote the code for it, but I did not use it at the end of the day. Basically, this method is about stuffing all the data into the context as well as the question and getting structured results about the documents, And I realized that it is too expensive. Let me show you something. Here are 3 requests that I did to Claude AI models, and you can see that here, all of them used 158,000 input tokens, And, let's see what's the pricing of Claude Opus 4.1. For the input, it costs $15 per million tokens. Let's see how much each request cost. So if we do 158,724 times 15 divided by 1 million, we can see that each request costed me $2.38, which is a lot, I basically bought $5 of credits on my Claude AI account, and then I expected that it would last for a very long time, just like OpenAI ChatGPT, right? Or OpenAI API. And basically, after like 20 minutes, I consumed all the credits. That's when I realized that it was too expensive. And I also did a cost analysis by basically counting all the input tokens and then, just visualizing how much it would cost me to do that. And let me show you the result of this simulation. So if I decided to evaluate all the 10 models, it would have cost me $166, you know. Just Claude Opus 4.1, it would have costed like $83, which is a lot. And all the rest of the models around $80 as well. When you know already that a method is super expensive, you just don't consider it, you just ditch it, because what's the point of like a client, you know, spending $50 per day on just like an AI that will answer questions? It's too costly, right? So when I realized that it was too expensive, I just, you know, discarded this method. But if you're still curious to know the code behind it, I will keep it available, you know, among the files that I will upload. So basically, here is the prompt, the master prompt, you know, that I used. And then here are the list of the models, and of course for each case we basically change slightly differently how do we make the API request. An important thing, guys, in order to run this code properly, I will also provide you with the .env file where you should write all your API keys for OpenAI, Anthropic, Gemini, and Cohere. Now, concerning the experiments that I've done, I have 39 experiments, you know, across all methods, and those are all the folders, you know, that correspond to the results of those experiments. And for every single experiment, we compute the recall for every single question, you know. Remember, we have 60 questions in our evaluation data set, and we also compute the retrieval elapsed time, but also some other time depending on the method. For example, the one that generates and executes Python, we compute the execution time of Python, you know, and we do the same for Cypher and so on. Apart from that, for experiments that involve LLMs, we also compute the cost per query. Basically, I just count the number of inputs in terms of tokens and the number of output tokens, and then since I know the pricing, I will just compute everything. And just so you know, I wrote some functions inside this util.py file where I have multiple functions here. For example, the one that is used to count the number of tokens, right? Another one that is used to clean the description, because remember, it uses, many descriptions use emojis and so on. It creates a lot of noise, and basically we don't want to add this noise into the prompt. So that's why many times I will be reusing this function, you know, to just clean the description. And here, as you can see, I have multiple dictionaries where I input like the pricing for the input and for the output. So as you can see, for example, here for this model, it's 5 cents per million tokens. And for some models, the price varies depending if we have more than 200k tokens or not. But as far as I know, I didn't use that because there was no case where I was using more than 200k tokens in my input. So let's see the first experiment about the symbolic retrieval, so the generation of Python code. I did 10 experiments, one for each model that is used, that you can see here. So as you can see, I tested Gemini 3, which is the brand new Google AI model. I also used the GPT 5.1, which is also pretty new OpenAI model. And I compared that with all the GPTs, the Geminis, and also this command model. And here's the code that corresponds to those experiments. So first, as you can see, we are loading the environment variables from our .env file. Here we are reading our CSV file, but we are also changing some stuff because remember, in each price, like it is not as like an integer data type. So that's why we need to transform it into a numeric. We need to do that for both the price and the door column. We also have some code here that is used, you know, to execute our Python code. And then we have the system prompt, where here I say you are a code generator. You'll be given a question about car listings, and your job will be to generate code to fetch data in the data frame, and so on and so forth. And basically here I provide the columns that are present inside this CSV. I also say here, which is very important, the code must filter and or aggregate using pandas, set the final output to a variable result, and also result must be a list of stock numbers as strings, and also results might be empty if no relevant documents are retrieved. Basically, I identify every single document by the stock number, which is basically the ID that is used by this business to identify a listing. And then here, very important, no printing, no imports, no file input-output, no comments, only pandas operations. Here I have this function retrieve via code, where basically we are making the request to the LLMs, and after that you have everything related to the logistics, to save and compute the recall of every single experiment. Here we are creating the folder, and here we are running the actual experiment. So basically, after creating the folder, here we are iterating over every single question. So for every single question, we will count the number of tokens, and basically the number of tokens is formed by the system prompt plus the question. And then we also compute the cost of the input, and then we generate the Python code, right? And then we compare the results, from the code that was executed with the ground truth documents that are, relevant to answer the question correctly. And then here this chunk of code is used to compute the recall, and then here we are appending in a CSV file every single data that you can see here, like all those columns. And as you can see, we do that for all those models, and we run this function run experiment for every single model. And then the CSV file at the end of one experiment, meaning one model, will look like this. Basically, we have the question, we have the actual context source, so the ground truth, and then we have the documents that were retrieved by the LLM and the code executed. And we compute here the recall. We also write here the code that was generated. So as you can see, this is the code that was generated. We have the model that was used, the number of tokens as input, and the number of tokens as output. And then here, as you can see, we have the column response elapsed time, which corresponds to the time it took for the LLM to get our response back. And then here you can see for the Python, for the execution time, it is almost instantaneous, like it doesn't take that much time at all, which means that most of the time is basically the response time from the LLM. And then here we have the cost of the input, the one for the output, and then here the total cost, which is just the addition of those two. And what I did after importing those CSV files into Google Sheets, I just did like an average of the recall, the elapsed time, and as well as the cost, just to get an idea. And as you can see, for GPT-5 Mini, we had a recall of 0.63. Now moving on to the second batch of experiments. For the cipher generation and execution, I did 13 experiments. So basically, I used the same models like in the previous method for schema number 1. I did 10 experiments for that. And then I took the two best models for schema number 1, and I applied the same thing, but I did that for graph number 2. And then the best of the best of everything so far was used for graph number 3. Now going on to the code, first, as you can see, we need to write the URI, the user, and the password that will be used by Python to connect to our local database so that we are able to run Cypher on it. Here I also wrote this function get graph schema, so that for every single graph schema I will get the type of starting node, and then the type of relationship, and then the type of ending node. And this was added into the system prompt so that the LLM were able to know what type of query to write. And guys, if you want to run the same function in order for this to work, you need to configure something that we call epoch inside of Neo4j, and let me show you how to do it. Once you open Neo4j, you just click on your database, And then here you can do plugins. Here you should just find install, you just click on it and then it will be installed. It's very easy. And here I have the graph schema that corresponds to every single one. Basically, as you can see, we are just copying and pasting the results from the function that I just told you about. So this is pretty long, you know, and it changes obviously from graph schema to another one. Here we have our system prompt, where I just start by saying you are an expert Neo4j cipher translator who converts English to cipher based on the Neo4j schema provided, and so on. And here I just also say that you'll be given a question about car listings and your job will be to generate, you know, cipher query. And here I just provide the graph schema, basically at the end of this prompt. And very important, I also specify here that you should return the stock number attribute of the listings and set it to the variable output so that I will be able to get the documents that were retrieved after executing the cipher query. Here guys, I just added like a test query where I just make sure that everything is working properly. Feel free to run it if you want by uncommenting this line and then running your code. Here we have the function where we run the actual query to our graph database. So the line that runs the query is this one, session.run, right? But before that, obviously we need a driver to be opened. And this is how we do it, using the URI, the user, and the password. And then, obviously, after running this query, we need to close the driver. And then the rest of the code is pretty similar, you know, to what we've seen using the previous method. Here, I just inform, you know, the graph schema, and then we just run for every single model. For the semantic similarity, I did 5 experiments, one corresponding to every single threshold that you see here. The reason I started with the 0.59 is that when I coded everything so that it starts to run, I just, you know, started playing with the threshold. And I've seen that by using 0.59, it was able to identify the 2 documents that are needed for the very first question, you know. I was just testing for the first question to see which threshold would be good. So that's why 0.59 was good. And then I just kept increasing that by 0.10 until we arrive to 0.99. So let me show you a little bit the code. The first important function is this embed function, where basically we are transforming text into vectors using this OpenAI model, which is called text embedding 3 large, which is, I think, the most widely used one. And basically the second other important function is this one, create and save embeddings. Basically this function replaces pinecone, because pinecone at the end of the day is what? It's just like somewhere like a place to store our numbers, our vectors. And the simple method to do that is by just saving a NumPy array. So NumPy is a library, is a pattern library that is used to manipulate arrays of data, and it is widely used in AI, machine learning, and deep learning methods. And basically, for every single listing, you know, we sanitize the description by removing all the noise. We transform that text into a vector via the embed function. We append, you know, this vector to our list of embeddings, and then after we are done, we just save those embeddings into a NumPy array. Obviously, I will be providing you with this NumPy array, which is called listing embeddings.npy. Then we have our function search with threshold that takes as arguments our query and the threshold. So by default, it is 0.9, but obviously you can use any threshold that you want. So at first, we load the embeddings by just calling np.load. And then here we compute the similarities, you know, between the embeddings and the query vector. So this is the most important line into this function. And then after that, we obviously keep the matches depending on the threshold. If the score is greater or equal than the threshold, method, we just add it to this list of matches. And then obviously what we want is not the documents, but the stock numbers. So I just, added another list, which is called results. And then we append all the stock numbers, which are in the matches list, into this results. Then the rest of the code is pretty much the same as we've seen already. Moving on to our next method, which is BM25. I did 5 experiments, one for each of those percentiles that you can see here. So as you can see, it is using this Python library, and the most important function in this file is BM25 retrieval. So it takes all our listings, as a dictionary, as a list of dictionary, and then we also use our query and the percentile. Here we initialize the BM25 model via this function here, and then we just tokenize the query, meaning we just split our document into a list of words, and then we use the function getScores to get the list of scores, basically. Here, after getting all the scores, we just use also the percentiles to determine the threshold, right? And then obviously we filter out all the relevant documents based on this new threshold. For our local cross encoder, I used this model, MS Marco Mini LM, and I also did 5 experiments for those percentiles here. So as I told you, I did that using this Python library called Sentence Transformers. And here, even though I just told you I use this model, we can also just play around with other models and see how it affects the recall. But I didn't have that many good results, with this method. That's why I didn't bother, trying to use some other architectures. The Cohere's re-ranker works pretty much the same as the previous one. I only did 2 experiments for this using those thresholds. And here the code is super straightforward. It is almost the same one as the ones that I've shown you. And here we are using the model re-rank version 3.5. And as you can see, the total cost is constant for every single request. That's how Cohere's pricing is. So it was pretty easy, to compute the total cost. And here, as you can see, even at first I thought about running multiple experiments for multiple percentiles, but since the results were not that good, I decided to not go ahead and run the rest of the percentiles. Okay guys, so now let's talk about the most interesting part, which is the results. And don't worry, I will be uploading all the CSV files corresponding to all the results, so that you will be able to look at it, and be able to analyze more thoroughly the results. But just know that the best results were from the symbolic retrieval, so basically generating Python code and then executing this code, and we had a recall of 0.78 with the model GPT 5.1. So maybe before watching this video you would think Gemini 3 would be so much better, but here the best recall was from GPT 5.1, and GPT 5 was in 2nd position with the recall of 0.71, and Gemini 3 was in 3rd position with the recall of 0.69. And you need to know that all the other methods, they performed poorly. Sometimes with the recall of 0.25, sometimes with the recall of 0.5, and so on. But the strongest ones were these ones here. We also had some encouraging results from the Cypher method with a recall of 0.66 using GPT-5 Mini. And you need to know, guys, that these results that I've got, like the 0.78, I didn't even optimize the prompts, I have some ideas that I will be doing in the next parts that will most likely improve the results. And let's see in more details the CSV file corresponding to the best results. So here, as you can see, the average recall is 0.78. The average number of input token is around 260. And on average, the output from the LM is from, let's say, 40 to 60. The response elapsed time was very good. Here it goes to 1.4, 1.7. Sometimes it takes some time, like 9 seconds, but overall it was pretty good. On average, it took 2.15 seconds for the LLM to get our Python back so that we can execute it. And as you can see here, this is the execution time from Python, and it is very fast. So most of the time it's from this response time basically. And you can see here that it costs on average $0.001 to query something using this method. Guys, I need to tell you something. During those experiments, there was also this Cloudflare outage, So many results were affected by this problem. And basically, it was the speed of retrieval that was affected. And I even took a screenshot where here they clearly say we're currently experiencing issues with the APIs, ChatGPT, and Sora. So basically, it proves the point that local models are needed, if businesses are serious about building a RAG and they don't want to depend on other servers, you need to develop your own model. And as I've shown you in some previous videos, it is not rocket science, like many people can do it. Another observation is that GPT 5.1 was better than Gemini 3, both in terms of accuracy and cost. For the cipher generation, Gemini 2.5 had the same recall than Gemini 3, but was costing less, obviously, which is a good point for Gemini 2.5, right? And also the graph schema number 1, so the most simple one, the most straightforward one, yielded much better results than graph schema number 2 and graph schema number 3. So this is always good to know. Another thing, maybe this was related to the outage, but Gemini 3 was super slow to run. Maybe it was also due to the fact that many people were trying it via either the API or the UI interface. So maybe that's why it was slow. I don't know, but it's not a good sign for Gemini 3, right? What I learned from this project is that a symbolic retrieval is much more adapted for data sets that have an inherent structure, And I would say that the vast majority of data sets, they have structure inside of them. So we need to seriously consider techniques like GraphRag and symbolic retrieval using Python to get accurate results. And guys, also don't fall for the hypes, because if we consider Gemini 3, you will see YouTube videos like, did Google just kill OpenAI? Or Gemini 3 just crushed everything, Basically, you have many YouTubers that are just riding the hype. They don't care about, whether really a model is better by testing or they just attracting views, and that's pretty much it. And also at some point Google introduced Gemini models that had a very long context, and you also had a lot of YouTubers that said that RAG is dead. Just like this YouTube video, Google killed RAG, and here you have in the description what happens to retrieval augmented generation when context windows reach millions of tokens and LLMs become cheaper, and so on and so forth. But, as I've told you, it is so expensive to do that. So yeah, this is just a hype train basically. So my main message is that the only way to know what the truth is to test. So just test and test and test again. The first method that I decided to boost is obviously the best one, which is the Python code generation and execution using GPT 5.1. So at first what I did is that I did a prompt optimization, and this resulted in increasing the recall from 0.78 previously up to 0.83. So what I did is that I added inside the prompt more rules to handle ambiguous questions. And I also reminded the AI that the goal is to fetch the relevant documents to answer the question. Not to answer the question directly, because many times the Python generated was about trying to answer the final question directly. And this is an example of an instruction that I added. For example, here a question involving low mileage means mileage less or equal than 30,000 miles. So this is about tackling ambiguous questions. Then what I did is a second prompt optimization where I increased the recall up to 0.88, where basically I included some examples of question to Python code. So basically the Python code that is supposed to be generated from examples of questions. And this is an example here. So I added if there is a question that compares multiple brands, we want to retrieve all rows related to those brands. For example, if the question is, how much does your Honda's cost compared to your Toyota's, the code output should be this one. And then I write the code that is supposed to be outputted by the LLM. And something extremely important, never ever guys include an exact same question that is in your evaluation dataset. Do something similar, but not exactly the same one. For example, this question here, the equivalent in the evaluation dataset is the following one. On average, how much does your BMWs cost compared to your Mercedes? So you see it is the same pattern, but not exactly the same data. So the LLM can learn how to generate the right Python code. Since this method worked well, I did even more of that, so I added more samples of question to Python examples, and this increased the recall up to 0.92, which is very good. So basically, with the same optimized prompt, I tested other models, and I ended up with two very good results. The first one with GPT 4.1 and the second one with GPT 5.1. With the 4.1, I had a recall of 0.95, speed of 2.98 seconds, and a cost per query of $0.003. With 5.1, I had a recall of 0.92, speed of 2.72 seconds, and a cost per query of $0.002. As you can see, we have a trade-off here, but the final choice depends on the context. But here, GPT 5.1 is better because, in this context, we can sacrifice a little bit of accuracy, or here recall, to boost, the speed and obviously the cost. And here, since we are not in a very sensitive industry like car dealership, we can make the sacrifice. However, if we are to apply this rack system to a more sensitive industry like health or law, in this case, we would definitely choose GPT 4.1 because we don't want to sacrifice accuracy and recall. The next step is that I thought, okay, the prompt is now optimized for maximum recall. So now let's try to optimize the time and the cost. So that's when I tried Grok models, not with a K, but with a Q. If you want to know more about Grok, you can go to grok.com, and basically it's an API AI service provider. They are known for their speed and cost efficiency, and basically they will provide you with open source models that are ready to be consumed. And those are either text models or audio, and Grok is a very cost efficient library that you should definitely consider for your RAG projects. Those are the text models that are supported. So you have 3 models from Llama, ranging from 8 billion parameters up to 70 billion parameters. And then you have 2 open source GPT models, one that has 20 billion parameters and the other one with 120 billion parameters. I tested all 5 of those models, but the Llama models were stopped even before the end of the experiments because they had very bad results in terms of recall. And basically after those tests, I had 2 winners. The 2 Gpt-OSS models. So for the 120 billion parameters, we had a recall of 0.935, a speed of query of 1.27 seconds, and a cost of query of $0.0002 per query. And then for the 20B model, we had a slightly higher recall of 0.943, a much slower response of on average 3.66 seconds, and around half the cost. But in this case, we will definitely choose Gpt-OSS 120B because while the recall is almost the same, a little bit lower, we are much better in terms of speed. In summary, for our boosting retrieval part, we went from OpenAI GPT 5.1 with the recall of 0.92 up to Grok with the Gpt-OSS 120B with the recall of 93, 1.27 seconds, a cost of 0.0002. So basically, by using Grok, we gain both in time, so 2x the speed, and the money, 10x cheaper, which is a lot. The second method that I tried to boost is the Cypher query generation and execution with the GPT-5 Mini. So what I did is basically I reused the same optimized prompt from the first method, and the results were the following. With the GPT-5 Mini, I had a recall of 0.9, 17 seconds in terms of retrieval time and this cost. And for GPT 5.1, we had a little bit higher of a recall of 9.1 and then a retrieval time of 7.1 second. So you can see that here, before any further optimization in terms of the model, on the prompt and so on, I needed to fix the Cypher execution time, because on average, it took around 4 seconds, to execute a query, which is not normal, because we don't have a big database and Cypher is supposed to be super fast, in terms of milliseconds. So I had to fix this before. And to fix the performance, I went to the Neo4j website, and here they recommend to install an extension called the Rust extension by running this command pip install neo4j-rust-ext. And basically I tried to install that in Python 3.10 and Python 3.12, and it was just impossible to install. Since I couldn't install those libraries, I couldn't benefit from the speed boost, So I just ditched, this Cypher execution method because it was too slow. And also I realized there were more risks with this method, because we run into the risk of generating a bad query with bad syntax. And let me show you what I mean. Here, this is an example of a query that was generated. So it starts with the match and so on. And here, as you can see, we have a random character that was generated inside. Normally, we're supposed to have a has name. So has underscore name and then everything uppercase. But here, as you can see, we have this anti/u200b character that is placed inside randomly. This was generated randomly by the LLM, which is bad, and the reason is that when you have multiple types of nodes and multiple types of relationships, you are increasing the risk of generating a bad syntax. So because of those reasons, I just ditched, this method. But even though I decided to not use this method, out of curiosity, I tried running a Cypher query using C#. So C# is my favorite language, it is super fast, and I noticed that on average, it takes 700 milliseconds to run a query. So this is a screenshot that I took after running a query using C#. Here, as you can see, it took 565 milliseconds to run, so super fast compared to Python. And I measured that C# is 5.7 times faster than Python. So guys, I thought that for next project, if I decide that GraphRag is the way to go, I will just use C#, as a programming language, and I will run everything using C# and I will show you how. And guys, if you want to know more about this method of doing it, just comment down below and it will be a very detailed project that I will show you guys. Now, for the generation method, at first I considered multiple methods, for example, chain of thought, and some other generation methods, but I thought, hey, we are trying to optimize the speed, of retrieving and generating an answer. At the end, I thought, okay, I will just go ahead and use the most basic generation method, which is just using an LLM. So basically crafting a prompt and then including a question and the context provided by the retriever with some clear instructions inside this prompt. There are two reasons why I chose this generation method is because it's simple. So it means it is simple to write. It is also simple to debug. And also adding too many steps would have an impact on the speed of the generated answer. So that's why this method I think is the best. Now, moving on to the evaluation metrics. Basically, I went to something called Ragaz, which is this framework here, guys. And if you go to docs.ragaz.io, we will find it. This is basically a library of code that helps you evaluate your RAG system, and it will provide you with multiple metrics and so on. And if you click on this link here, available metrics, you will see all the available metrics that they came up with. And here for our case, for the generation, we have two that are interesting. This one here, the answer faithfulness, and this one here, the answer relevancy. But then I figured that both of those metrics are not well adapted to this use case. And I will tell you exactly why. But guys, as a RAG developer and designer, it is your responsibility to not apply stuff blindly, basically, and to choose, the most well-suited metrics for your RAG project. First, let's see how does answer relevancy work. We first take the generated answer, we generate 3 possible questions from it using an LLM, and then we transform those questions into their embeddings, and then we compute the cosine similarity between the generated questions and the actual question. And the underlying concept is the following one. If the answer is relevant, it means that we can easily reconstruct the question from it. Now, why this metric is bad? Let's see some examples of answers inside the evaluation dataset. We have, for example, this one. We currently have 24 vehicles under this category. Would you like me to narrow it down, and so on and so forth? Or this answer, it runs on gas. Would you like to know more about its features? So basically, many times it is impossible to reverse engineer the question only from the answer. That's why this metric has to be discarded. Now, let's move on to the second metric, which is answer faithfulness. The way it works is that we first take the generated answer, then we break it into multiple statements, and then for each statement, we verify if this statement can be inferred from the given context. And basically, it measures how consistent a response is with the context. Now, why this metric is also bad for our use case? Multiple questions answers have an empty context. Why? Because we want also to test the RAG system to be able to say, I don't know. We want to test those edge cases. For example, an answer could be, I don't have information about accepted payment methods. You'd need to email the dealership directly. So that's why answer faithfulness is to be discarded. But the thing is that, okay, we are discarding those 2 metrics, but how to actually measure how good an answer is? The first answer is by using an LLM as a judge. It's basically measuring only the answer quality, and basically we are using a prompt and an AI agent that will give a score between 0 to 1 to the generated answers, and it will also give an explanation of the score. At first, I didn't use an explanation, but I thought that it will be useful to add in the answer, because we want to iterate, we want to improve the prompt, and it is always good to know how the LM judge came up with the score, so that we can see if it is too harsh or too lenient, and so on. I also came up with another metric that I called RAG efficiency score. It measures the end-to-end RAG pipeline, because obviously we don't want to evaluate only the generation part. It basically uses the recall, the score by the LLM, the time, and the cost per query. And it is computed via this formula. We take the score answer, we multiply it by the recall, and we divide it by the time plus the cost per query. And we want this ratio to be as high as possible. And it measures how efficiently the pipeline converts retrieval plus answer quality into performance per unit of cost and time. And then the third method that I used is human as a judge, basically me, because I realized at some point that it was too tedious and costly to keep improving the prompt of the LLM judge. That's why after I got some scores by the LLM judge, I would manually correct those scores as a second pass, basically. Now guys, before I show you the results, I need to tell you that while getting some results and reviewing the answers generated, I slightly modified the evaluation dataset. I realized there was one question that was actually better answered by the LLM than me. And basically, the answer was buried inside the description rather than being part of the specs. And let me show you exactly what I mean. Here in line 33 of the evaluation dataset, we have this question. Between your 5 cheapest SUVs, which one has better highway MPG? And this is one of them, one of the 5 cheapest SUVs. And as you can see here in the list of specs, we don't have any information about either highway MPG or city MPG. And it was the same case for the rest of the SUVs. So I thought, okay, the best possible answer that could be generated is none of those SUVs contain information about highway MPG, you know? But the thing that I didn't realize is that this information was buried somewhere in the description, right? And the best possible answer which I replaced in the dataset is this one, which is 2010 Chevrolet Equinox has the best highway mileage, and so on and so forth. The second question that I fixed is this one related to heated seats. So I think the question is about which of your sedans contain heated seats or something like that. And basically it's the question at line 22. And you know, when I generated some Python code to fetch the actual answer, I just searched for the keyword heated seats. So I ended up with only one car. However, I realized later on in the dataset that there are multiple ways to express heated seats. You have heated front seats. You can also have heated and ventilated front seats, right? So after fixing this, I realized there were actually 27 cars, you know, with heated seats. That's when I changed both the answer and the context source. So guys, you need to pay attention to those details if you want to craft a very high quality evaluation dataset. And many times, even if you think you have already like a high quality of dataset, when you will start generating some answers in your RAG project, you will realize that some answers could be improved. Now, the first result that I got with GPT 5.1 is with the score answer of 0.66, so an average one over all the questions. And the thing is that at first it doesn't mean anything, you know, when you have this answer. It could mean a good thing or a bad thing, because it could be like a too harsh LLM judge, or it could be a bad generator. But either way, we need to improve the LLM prompt. And then after optimizing the prompt, but not at 100% level, I got those results. Using GPT 5.1, I got a score answer of 0.79, a recall of 0.91, a time of 3.53 seconds, a cost per query of $0.009, and a RAG efficiency score of 0.23. And then using Gpt-OSS 120B, I had a score answer of 0.80, a recall of 0.94, a total time per query of 2.88 seconds, a cost per query of $0.001, and the RAG efficiency score of 0.31. And you need to know that those score answers here are the final score after the LLM as a judge as well as the human as a judge. And obviously the prompt could be optimized further to get very good answers by the LLM. So now guys, let me show you the code to generate an answer and also the code for the LLM judge. When you will download my code, in order to run the whole RAG pipeline, you will have to run this file here, run_rag.py. And this contains everything that you need to run the end-to-end RAG pipeline. So we have this function here, generate answer, that I wrote. It basically uses a prompt where I start by saying you are a sales rep for a car dealership in a conversation with a lead, and so on. I provide some rules here about context, style and tone, price related questions, and so on. And then obviously I provide some good and bad examples, you know. And at the end of the day, we are using a question, the number of listings, and all the listings as the context source. And this is the function judge answer that I wrote that is used to give a score between 0 and 1 to a generated answer. And the AI model used as a judge is GPT 5.1. So similarly, here we also have a prompt where I start by saying you are an expert judge that evaluates the correctness of AI generated answers of a RAG system. And then obviously I also provide examples of good scores, bad scores, some scores that are close to 1 but not quite yet, right? And also here even more bad scores. And as I told you previously, this LLM will be using the question, the generated answer, and the expected answer. Now let's guys talk about some tips that I have for you if you want to implement your own RAG system. First, if you are in the step of optimizing a prompt, first use cheaper models, like GPT-5 mini, and then switch to better models once the prompt is fully optimized. And then in order to improve the prompt of the generator, first go and address the answers with bad score, meaning either 0 or near 0, which have a recall of 1. It means that the retriever was able to get all the relevant documents. However, there was something wrong with the generator that wasn't able to generate a good answer. And then for your project, if you want to use Grok, you need to unlock the developer tier to disable the rate limits. Another thing is that if you want to also be the human judge for your RAG pipeline, go first for the answers with high scores, meaning either 0.28 or 0.95 with a recall of 1. Because many times I realized that the LLM judge was too harsh, and instead of just giving 1, gave a score of 0.8 and 0.95. So I had to manually cover all those answers and just tune the score and change it from 0.8 to 1. Another thing, guys, is that you might still get bad results even if you have a recall of 1, because sometimes from the retriever you will have a low precision, meaning that even if all the relevant documents are retrieved, the retriever will also add some noise, some irrelevant documents. And this will just mislead the generator, and the final generated answer will be bad. Let me show you an example of this. We have here in question 12, what's the most recent SUV that you have under $10,000? And the context source concerns only one listing. So here we have only one stock number as our ground truth. However, the retriever found 2 documents, and among them the right one, which means that we have a recall of 1 but a precision of 0.5, which means that here, even though the expected answer is our most recent SUV under and so on is a 2019 Mitsubishi Outlander, here it will say we have 2 2019 SUVs under $10,000. So as you can see, the generated answer is very bad, even though the recall is very good. Now for the chat interface integration, I used Claude AI to provide me with the boilerplate page made of HTML, CSS, and JavaScript. Let me show you how it looks like. So this is how the end result looks like. Basically, you have the main title here, and then you have a first question from the AI, and then you can ask any question. A first example of a question could be, do you have 2020 Toyota Camrys under $20,000? Yes, we have 2 2020 Toyota Camrys and so on. And as you can see here, I also decided to add a RAG stats part so that it will display the response time. So as you can see here, it is 2.84 seconds, and it is divided into the retriever time and the generator. We can see that here the retriever is taking a little bit more time, the number of listings that were used to generate the answer, the cost per query, made of the cost from the retriever and the cost from the generator, as well as the number of tokens that were used. So here the number of input tokens and the number of output tokens. In Claude AI, this is the first prompt that I used. Here I write, I designed a RAG system that takes as input a question for a car dealership and outputs an answer for that. I want to design an HTML CSS page for that chatbot. But the thing is that at first it's provided me with a bad result, something that doesn't have a good look and feel, But then I kept refining the prompt and tell him to add more stuff. That's how I came up with the final result. Let me show you how the HTML looks like. So this is the page that was generated. We have here the part for the CSS, so basically the colors and everything. We have here the HTML elements. So here this part for the chat interface. Yeah, this one. And here this part for the stats panel. And this part concerns all the JavaScript that is required to display the animations, to also send our question to the server, and then get back the answer from the server and then display it as an answer from the AI. The main functions are here send message, which is used, to send our question to the server and then display the result that the AI is supposed to display. And the most important function is this get response here, because this is the one that interacts with our server, that will go and then call our Python functions for the retriever, the generator, and then getting our final answer plus stats back. So this is the endpoint that we call. It is called process question. Now let's see how it looks like from the server side. As you can see, this is the server that I created for this RAG pipeline, and this is the endpoint that gets called. It is a simple UV-corn server that uses fast API for the API routing, and as you can see here, this is the main line that is responsible for generating our answer from the AI. To run the server, you just have to write this command here, UV-corn, then between double quotes, rag_server, and then app, and then -- reload. And the HTML file that I showed you previously needs to be under this folder, HTML folder, where we should have rag_interface.html and then wheel.svj. If we go back to the server, this line here uses this file, which is called rag engine premium cars fl. And basically this one is about generating the answer. This file contains the strict minimum code that is necessary to run the generator. And as you can see, this file is also importing the function that is used for retrieval. We combine everything into this function that I called run rag pipeline, that as you can see uses the model retrieval, the model for generation, and the question to generate our answer. Obviously, in addition to the answer, it also generates all the stats that are displayed in the HTML. Now guys, I want to talk a little bit about AI voice integration, just a high level view. So what I would do if I wanted to basically host and integrate this RAG into like an AI voice agent, I would first host the server into a VPS. I'm very familiar with Hostinger, so this is the go-to provider that I would use. And then I would also use Retail AI for the AI voice API because it's very easy to use. And if you guys don't know them, just go to retailai.com and you will see that it's super simple to use. You can even try a live demo here. They have a clear documentation about how to use their API and so on. Now inside Retail AI, what I will do is to include a function call inside the AI agent, so that we can call our RAG in the VPS that hosts our server, and then we can get our answer and then tell it back to the customer or the lead during the conversation. And then obviously to gain trust and have a high degree of confidence about the robustness of our system when we deploy it for live environment, what I will do is to do automated testing, which is about creating an AI voice bot that will be the tester, that will be calling our AI voice bot that we just created that is using the RAG system, where we want to measure multiple metrics. For example, the latency of each call, the average RAG response time, and so on and so forth. And what I will do, since we already have an evaluation data set, we could trigger one call per question, then make the caller ask a question, and for each question check whether the answer is good, and then check all those other metrics I just told you. So that was it guys. I hope you enjoyed it and learned a lot from this video. So to access the full code, you will have a Discord link in the description that you can go through to access everything. Now guys, when downloading the code, you will be able to download the zip file for every single part of this project, but obviously basically the last part, which is about running the end-to-end RAG final pipeline. And yeah, obviously let me know if you want, if you have any project in mind and you would like me to cover it next. And if you're a business owner and you feel like this system could definitely benefit your business, feel free to book a meeting with me via the link in the description. Cheers, guys!